Good morning, good afternoon, and welcome to this webinar on arc flash protection. Let's see. Now, so my name is Kenneth Nyman. I do work as a product line manager in ABB's Distribution Solutions in Finland. And together with my colleague Rainer Harju, we will guide you through the arc flash protection today. Our contact information are on the slide, and this will also be shown in the end of the webinar, so you can write them down afterwards also. And please contact us if you have any questions at some stage. The agenda today looks like this. We have roughly 40-45 minutes of time for the presentation, and then some questions. So in the beginning, we will have a look at the arc flash phenomenon as such, how an arc flash occurs, and what kind of effects it has. Then Rainer will introduce our arc protection system REA 101. Then we'll have a look how to do arc protection if we integrate the function into modern protection relays. We have a look at some solution examples and how to build systems. And in the end, we'll have a summary and Q&A. And as Sonia said, during the presentation, you have the time or the possibility to ask questions directly in our chat. And in the end, we will go through them, depending on how active you are and how much time we have. So we will pick the questions and go through them in the end of the seminar. So let's get started looking at the arc flash phenomenon. So what is an arc flash? It's in short, it's an explosion. It's a result of a rapid release of energy due to an arcing fault, which can occur between phases, or phase to neutral or ground. An arc arises when at least one part of the current passes through a dielectric, which is usually air. Consequences of an arc flash are quite severe. As it's an explosion, you have an uncontrolled release of energy. It can be up to 40 megawatt. The rapid pressure rise inside the switchgear results in a fatal blast pressure wave that can reach several meters away from the switchgear. Explosive release of arc plasma, which with very high temperatures, up to 20,000 degrees centigrade, molten metal fractions and shrapnel that flies around the switchgear room. Toxic gases as metal vaporizes are also present in the switchgear room. There's a very intense light and a high acoustic stress level, which are damaging your eyesight and your hearing. So if we go over to reasons for internal arc faults, it can basically be divided into three different parts. We have the human related, the technically related, and the environmentally related reasons. If we go through human related reasons, working on energized equipment, either unintended or in worst case intendedly working on energized equipment, which is also linked to this one, disregard of safety rules. So you are working on energized equipment and you know about it. A very common reason for arc faults is forgotten tools and equipment in the switchgear, which lead to arcing faults when you switch the switchgear back on. And installation faults, also poor workmanship, for example, on cable terminations, busbar joints not correctly tightened, etc., can cause arc faults. Then on the technically related, we have examples like equipment faults. And equipment faults tend to increase by aging and wear. So if you have old equipment, the risk is higher. Over voltage, overload, overheating, and all this can also cause internal arc faults. If we go to environmentally related reasons, moisture and dirt, which causes then a reduction in the creepage distances and poorer connections, can cause arc faults, corrosion, vibrations that are loosening joints and bolts, and also animals getting into the switchgear or switchgear room and causing short circuits with their bodies, or by damaging isolation and cabling, control cabling, and etc. So here's some examples how it looks when you have had an internal arc fault in the switchgear. So on the left side here we see medium voltage switchgear where you have had an arc fault in the busbar compartment up here. The fault has spread also, or the effect of the arc has spread also to the nearby cubicles, so also in the cable compartment here. So you see quite a lot of damage here. In the middle we have a circuit breaker that has been racked in the closed position. It has been racked out for testing purposes. It has been in closed position and racked in, and by overriding or breaking mechanical interlocks, it has been racked in and getting close enough to busbar with 20 kV and earth. And if you get close enough, you will have a flash over. And here you see that even the tulips have molted of the energy that you have in the flash. On the right side, we have a picture from the cable compartment where you see where the cables should be, but the cables have burned up and melted in this case. The earthing bar, the copper bar has deformed and melted, and also the damage on the steel construction itself is severe here on the sides. If you look at more impacts, so the whole buildings, like here on the left side, you have had an arcing incident in the cable compartment on the right-hand panel. Due to the power in this and the effect, even the wall has collapsed in the building. So the power is quite high here. On the right side, the building itself has survived, but it has blown off the roof, and you have had a severe fire inside the building also. So what can we do to prevent this then? As our webinar says, also time is critical. So we need to reduce the arcing time. Here's an example of a similar test. On the left side, we have an arcing time of 500 milliseconds, so half a second, which is quite typical for an overcurrent protection, for example. You have severe damage inside this one, but on the right side, we are reducing the arcing time to about 35 milliseconds by implementing an arc protection device. And you see the damage is significantly lower. And why does the time matter? In this case, looking at the curve, we see that the energy is increasing exponentially, and the damages are getting bigger and more severe after about 100 milliseconds, 150 milliseconds. You will start to have copper fire, so the cables are burning, bus bars are burning, and the steel construction starts to be damaged after about 200 to 150 milliseconds. So in short, if we are in the green area here where we are looking to be with arc protection, we will have limited personal injuries, and the switchgear damage is very, very little and not worth mentioning. So with arc flash protection, we reduce the risk of personal injuries, and the damage on the switchgear is significantly then lowered. There are of course different ways of handling arc flash mitigation. For example, modern switchgear we have built like that, as designed like that we deflect possible arc flash energy is deflected from the switchgear away from the user. Or then what we will look more into now is to reduce the arc flash energy by implementing arc flash protection, and that's something we'll look more into detail now. So I will give over to you, Rainer, to look at the REA.
Thanks, Kenneth.
Let me see. I give you the. No. Just a minute. I need.
Sorry. Okay. Yeah. Thank you, Kenneth. Arc faults are the most dangerous faults that you can imagine to happen in power distribution, and especially in switchgears. And today we are looking especially medium voltage switchgears and how to protect them. REA, arc protection system, is one of the key elements in ABB portfolio now when it comes to solutions we can provide for arc fault protection. ABB has a long and successful track record of providing active arc mitigation devices based on optical detection of arc flashes. And let's now look closely at the REA arc fault protection system and the components of it. The REA arc fault protection system consists of the main model REA101, and it can work as such as a standalone device, and the basic system can be just built on one REA101 and sensors, or it can then be extended with 3 types of extension units. And in the next slides, I will go through briefly all of those. And the REA arc fault protection system is targeted to customers who desire to keep the protection system separate from the main power system protection, and that is the normal protection relays. And it can be used in retrofit and greenfield investments. As Kenneth already told, the arc flashes causes very intense light, and so the optical arc flash detection is one of the most effective way to detect the arc flash and to provide protection with the speed of light, so to say. For optical arc flash detection in REA system, we use either naked fiber loop type sensors. Those lengths can be up to 60 meters, or then another alternative is to use lens sensors. They are more retrofit friendly to install, but the loop fiber loop type of sensor, it has a benefit that it can be supervised with a light test pulse periodically. The lens sensors are not supervised in REA system. But on the other hand, lens sensors have the benefit that if certain lens sensor has react and it's indicated by the REA system, then you know the location where the arc fault took place. Additionally, we secure and we recommend always to secure the optical arc fault detection with simultaneous overcurrent, and REA 101 unit has instantaneous independent overcurrent or ground fault current detection. There is a possibility to use only light detection without overcurrent detection, but since some spurious light can then cause unintended operation, we recommend to secure the optical detection with simultaneous arc fault current detection. I say detection because it's not a protection function. It's just an additional securing method for light detection. And then we have, as we heard, time is critical in arc protection. We have also fast solid state trip outputs to give as fast tripping as possible. Mechanical contact output relays are not that fast, but we have a solid state trip outputs which are directly capable to trip circuit breakers. And to secure the tripping, we have also integrated circuit breaker failure protection feature in REA system. Then, if you would like to extend the system, and then you can use multiple REA 101 units or add some extension units, and so to get several sensors and also then create so-called zone selective protection system. All in all, REA 101 system operates in less than 2.5 milliseconds. This fast operation speed we can achieve no matter how many REA 101 units we have in the system or how many extension units we have in the system that pick up and detect the arc light and simultaneous overcurrent. Circuit breaker tripping is initiated in 2.5 milliseconds or less. The arc quenching takes place when the circuit breaker has operated, and in medium voltage circuit breakers that takes typically 3 to 5 cycles. Let's now look closely at the main unit. It enables redundant, instantaneous, and fail-safe arc fault protection. I mean it's redundant because it's an additional protection to normal overcurrent and arc fault protection relays. It's instantaneous. it doesn't have to be time coordinated with other protection relays, and it's fail-safe because it has very comprehensive self-supervision. The main benefit of a RER protection system is that it minimizes material damage and increases operating personnel safety and allows smooth power restoration. It's easy to set with dip switches. You don't need any tools, setting tools. All the settings are done by the front panel switches of the modules. Then let's look the RER 101 from the back. There we have input ports for the fiber sensor. For one arc loop sensor can be connected as a loop so that the both ends of the fiber is connected to the relay, or then we can just connect the input end and let the other end loose, but protect it carefully from light. And so it forms a radial type of fiber sensor. Or instead of loop sensor, we can use just one length type of point sensor. We have also current inputs, three-phase current from protection core CTs can be connected to RER 101. And we have both 1 amp and 5 amp rated inputs. Then we have two high-speed solid-state tripping outputs for direct tripping and of circuit breaker, and they are so fast they can trip already in 1 millisecond. One conventional trip output, we have also electromechanical relay contact to provide, for example, circuit breaker failure protection, or it can be used as an alarm output. Then for panel flush mounting, we have an accessory sealable front cover, just transparent polycarbonate cover, and it's an accessory. And now for each RER 101 main unit, even 10 extension units can be daisy chained. 5 ports to port A, and another set of 5 extension units to port B. So altogether 10 per each RER 101. Additionally, we have a optolinks facility, and via these optolinks we can then extend the system by adding more RER 101s to communicate with each other, and via those optic links, fiber optic cabling, we can communicate either light, overcurrent, or trip signals. The standard model has this kind of connectors for plastic fiber cables, but then we have another model with the glass fiber optic connectors, and with that model we can provide communication links over very long distances, even up to 2 kilometers. And practically unlimited number of RER 101 units can be linked together. to form such a system. The biggest amount of system I have heard about that has been built with this optolinks is that 50 Relion units has been connected as a ring, and they communicate over current to that ring type of network. And so very wide systems can be built up. Then let's have a short look to those extension models. There are three types of them, and they look quite the same to each other. REA103 provides two fiber sensor inputs, and so the detection range of the main unit can be extended with using these units. Here we have also alarm contact outputs, so one for each sensor, and self-supervision is also monitoring the operating voltages and integrity of the sensor fiber loops in this unit. REA105 is interesting model and very popular nowadays. And why is that? Because it has similar high-speed solid-state tripping outputs as the main unit. And here in this model, we can have one sensor connected to it. So with this model, we can trip separately different busbar sections or feeder cable, or to provide this for feeder cable compartments, and then we can selectively trip the outgoing feeders, for example. And the last extension model type is REA107, and to this we can connect 8 lens type of sensors. These lens type of sensors are especially suitable for retrofit installations. Some have experienced that installing especially very long fiber sensors as loops might be challenging to route them and through each and every compartment, but these lens sensors are more handy in that respect. This unit has separate LED indicators for each lens if they have detected light, and here we have also alarm contact outputs. Yeah. One final word about these models is that I would like to emphasize that it's good to utilize the alarm outputs. If it happens that the extension model has detected light, how you get to know about it, although it has not definitely caused a trip because no overcurrent has been simultaneously detected by REA101 unit. But it's good to connect these alarm outputs to, for example, to some relay binary input, and so to get alarm from there. Sometimes it happens that some not ARC-related light has caused the rare unit to detect light, but then you can take actions to find the reason why it happens, although there's no real ARC, if it goes to binary input of protection relay. And then you can get alarm also to SCADA, for example. Okay, that was in short the REA system and the model sheet has.
Okay, thanks, Reinhard. So I will take over here. Let me see. So now a few words about ARC protection integrated into the Relion protection devices. So ARC flash can also be integrated directly into the normal modern protection devices, like for example the ABB's Relion REF615 or the multi-application device REX640. By integrating ARC flash into the normal protection, it's a very cost-effective solution. If you're anyway changing the protection relays, you can add on ARC flash protection. The installation is quite easy to do at the same time with the protection relays by utilizing the lens sensors with short connections only. The engineering is done at the same time as you engineer the other protection functions, so it's quite easy, and also gives a lot of possibilities to do selective schemes and different functionality in the same engineering as the other protection functions. In the integrated ARC flash protection into relays, you are also using the same philosophy as in the REA, that either you trip with only light or light and current criteria. The integrated ARC flash usually uses IEC 61850 Goose to communicate between the different devices. So if we look at our offering, the Relion 615 and 620 series, we have 3 different sensors, and the ARC flash is the ARC flash protection is optimized for single busbar applications. So here on the right side, you see a cross section of a medium voltage panel, metal enclosed panel, metal clad. You have the 3 sensors which you see up in the picture, same sensors as in the REA system. You have sensor number 1 in the busbar compartment. So on the simplified single line you see here. Number 2 is the circuit breaker compartment, and number 3 the cable compartment. This means also that if you have an ARC flash somewhere here, you will have a indication also on the relay itself to see which sensor has indicated. So it helps quite a lot to find the arcing point. There's a automatic reference adjustment for the background lighting, so that's not influencing the function. And operating times are a bit slower in the protection relays than in the dedicated REA system. We talk about 10 to 12 milliseconds with the mechanical outputs, and if we use high-speed outputs as we recommend, the tripping time out from the device is about 4 to 6 milliseconds. Then of course the circuit breaker time, 30-40 milliseconds, is added to that one. If you look at the REX640, here we have an example of that one. The 640 is a multi-application protection and control device, and This one is optimized for single and double busbar applications due to the fact that we have 4 sensor inputs in the device. So again, the cross section of a double busbar panel. So you have sensors 1 and 2 are the busbar sensors. You see them on the picture also. Number 3, circuit breaker compartment, and 4, cable compartment. So again, you have a possibility to do the selective protection here. One benefit that the 640 has is that the sensor inputs can use either loop or lens sensors, and both are supervised. So you always have a supervision of the lens or the sensor loop. Tripping times are similar to the 650 and 620 series, so 10-12 milliseconds with normal mechanical output and around 5 milliseconds with the static power output. If you look at the sensors available, we have different sensors available for both the REA system and also for the REX640. So we have different lengths of the lens sensor cables and also of the loop sensor. We have up to 50-60 meters of a fiber loop that can be installed throughout a switchgear, for example, which is quite cost-effective solution if you want to protect the whole switchgear with one loop. The communication, as I said, is usually done with IEC 61850 and goose communication between the devices. You can also do it with binary signals, but then you have to remember that that's a bit slower due to the mechanical delays in inputs and output contacts. Goose communication is optimal for this because it's also supervised the connection between the relays. So here's an example of a simplified example of how it works with the protection relays. The protection relays, of course, have the normal protection functions over current, cert faults, and so on. And additionally, then arc flash. So if you look at the relay B here, for example, if that one detects light in the busbar compartment with the sensor number 1, it will send a message over goose to the incomer relay that I have received light. This one is checking the criteria if it's programmed to also use the current criteria. It's checking that, okay, have I got overcurrent on my incomer? If yes, it will initiate a trip on the Q01 breaker to de-energize the busbar in this part. In the same way, if the relay B sees an arc flash in the own cable compartment, with sensor number 2 here, for example, it will look at it, and according to the programming, it will usually then trip the own circuit breaker and just de-energize the cable compartment, and the rest of the process is up and running still and energized. So this is very simplified picture of how to build it. Then you can program whatever functionality you want to have, because we are quite free in the programming then. So, as I said, this simplified, more detailed, and more applications will be covered by Rainer. We'll give over to you, Rainer. Just a minute, I give you the.
Yeah, thanks, Kenneth. Now let's look more solutions. We are targeting medium voltage switchgears and such AIR-INSULATED switchgears segregated with compartments. And here is an example of UniGear ZS1 panel. Protection relay is here in low voltage compartment. Then we have different compartments busbar compartment, apparatus compartment for circuit breaker, and cable compartment, which includes current transformers and voltage transformers. The switchgear is built up from several such panels. Here we have an REA, arc fault protection system, and it's a typical main-time-main construction, what is described here. We have REA 101 units for both incomers, and we are sharing the overcurrent via optical links between these REA 101 units. So, for example, it can happen that only one of the incomer is feeding, and let's say it's, for example, this breaker is closed, and on this side it's open. So how for the fault occurring here on this busbar section A side, how can it trip if it needs also overcurrent? So this relay detects the overcurrent and sends it to this relay on the left side, and then it can trip. Then we have also REA 105 extensor units, and those are used here to measure the busbar section arc faults and lights occurring there. Additionally, we use REA 105 units for each outgoing feeder cable compartment, and they can detect the arc occurring there and trip only their own outgoing feeder circuit breaker if the main unit provides simultaneously overcurrent. The main units provide via cabling the overcurrent information to these extensor units, so they can trip, and they via this daisy chain cabling they get also auxiliary voltage, operation voltage. Here, these REA 105 units that are monitoring busbar sections, they are configured to set via this cable to the main unit the light indication. So the main unit trips it if it detects simultaneously overcurrent. And every time the main unit trips, it forces also the connected REA 105 units to trip. So if the fault occurs here in busbar area, of course also the tiebreaker has to be tripped, and when this main unit forces all REA 105 units to trip, they trip also the tiebreaker. Then another example is here, the same basic signal line diagram, but instead of optical links, we use REA 105 units to communicate the overcurrent information. It goes to both directions via those connection cables. But otherwise, this is very similar as the previous example. Instead of loop sensors for such a small compartments like outgoing cable termination compartments, we can we can use lens sensors. And even for the main units, we can use lens type of sensors instead of loop sensors. Then additionally, for arc fault protection, ABB offers so-called UFES, ultra-fast earthing switch, and it can be combined to REA system. And this is targeted to customers for whom arc faults and associated power outages can cause extremely high negative financial impacts. And it is working together with REA. The REA system provides the arc detection, and then this system is connected to it. The UFES can be installed as a service box on the side or on top of the switchgear or as a truck unit. And here's the operation principle. REA 101 unit sends by optolink fiber the trip signal to this so-called quick release unit, and then it commands the primary switching elements to make ultra-fast galvanic earthing of the busbar. And the arc is quenched in 4 milliseconds as the busbar voltage collapse as a consequence of this galvanic earthing. And then REA 101 unit trips the circuit breakers later on. But the arc is killed already in 4 milliseconds. So long before the arc fault can cause excessive damages or any danger to personnel. Then we have also possibility to provide solutions with integrated arc fault protection in Relion relays. So with the REF615, REF615 or REF620 series, or with our high-end relay REX640. And here is an example of the similar system as we saw in previous examples with REA system, but here now with the Relion relays. Relion 615 relays, they can use lens sensors, and those 3 sensors what you can have in 615 relays, you can put 1 to busbar compartment, 1 to circuit breaker compartment, and 1 the outgoing feeder compartment. And then if the fault happens, for example, here in the circuit breaker compartment, this relay detects it and sends the signal via goose to other relays, and command it also to trip the tie breaker or bus sectional breaker. Here we have REX640 relay at the incomer, and it's also used for transformer differential protection of the incomer transformer. So we get overcurrent from the high voltage side, and that we can use as an enabler for arc fault protection. Using these relays and the causal information sharing between the relays, we can also build a selective tripping scheme. If the fault arc light is detected in busbar section A here, then it's sent to incomer relay and to incomer relay. So this relay trips the incomer circuit breaker. Depending where the fault is, then we can share the signals, the arc light detected signal or trip signal to other relays, and then we can either trip or log out if the circuit breaker is already open, depending where the fault had occurred. And only the minimum area is tripped. So this means selective tripping. As a last example, here's very similar as the previous one, but here we are using fiber loop sensors with REX640 relays on both sides. Both busbar sections are protected by loop sensors, and also the bus riser compartment. That's briefly some solution examples with Relion relays and with real system.
All right, then I think we have as a summary just a reminder that by investing in arc protection, we do protect the personnel, because most accidents are caused by human errors during maintenance or repair work, and also increased risks due to varying age equipment and increasing power consumption. So we will have maximum protection with arc protection, and also protect the assets to limit damages caused by arc faults, to extend lifetime of older equipment, and also flexible planning of maintenance, so to have maximum uptime with arc protection. And all this leads to maximum peace of mind, hopefully.